This next result will take us towards something called Hermitian adjoint of a linear operator, which is used in quantum mechanics. One day when we will start quantum mechanics, we will see how it's used there. So anyway, let's first see this result. So as usual, we have a linear operator T on a finite dimensional inner product space V. Then, given any vector V in V, there exists a vector W in V depending on this chosen vector V and that linear operator T, such that the inner product of the image of U under T and V equals the inner product of U and W for all vectors U in V. Such a vector W will exist for that T and this vector V. And moreover, this vector W is actually uniquely determined by V and T. Let's now see how to prove this. The proof starts with this claim that it's sufficient to exhibit such a vector W which works for all the basis vectors of our space V. What does that mean? It means that it's enough to show that this equation is true, where in place of U we just have the basis vectors of our vector space V. Why? How exactly is that sufficient? Let's see. So this part, which is only for our own understanding, has been kept confined within these dashed lines. It's not exactly a part of the proof. Suppose that our vector space V is two-dimensional, that it has this basis consisting of the two vectors U1 and U2. And what we are claiming here is that if we can show that this equation is true for U1 and U2, that's enough. That means we now have U1t, V equal to U1, W and U2t, V equal to U2, W. How is that enough? Because this is a basis for our space V. So any vector in this space is going to look like this: alpha 1 U1 plus alpha 2 U2, where alpha 1 and alpha 2 are scalars, complex numbers in general. And then using these two equations, this is what you get. On alpha 1 U1 plus alpha 2 U2, if you apply T and use the fact that T is a linear operator, so that T gets distributed over this linear combination, and then you use the linearity, everything you know about an inner product, and then you use these two facts, you will see that ultimately that same equation is also true for this general vector. That is why it's only, it's enough to only prove that this equation is true for basis vectors U. So that reduces our work. So now we are going to proceed to do just that. So the proof next proceeds to consider an orthonormal basis for our space V. Because V is a finite dimensional inner product space, say n dimensional, it has an orthonormal basis consisting of these n vectors U1, U2 up to Un, which we already know exists from the theory of inner product spaces, finite dimensional inner product spaces. Now this is the W that we are proposing. This linear combination of these basis vectors Ui, where the coefficient of Ui is the complex conjugate of the inner product of Uit and V. V is our that V, okay, and Ui of course is one of the basis vectors. Now will this W work? Let us see. So next what we do, next we choose an integer j between 1 and n in this manner. That means j can be 1, it can be n, or it can be any integer in between. And we consider the inner product of uj with w. Actually the equation that we want to show for uj in place of that u, we are starting with the right hand side of that equation. So that is why we are writing uj, w. And then we write what w is this linear combination. And then I have actually not written, I should have written two steps, but I have done it at once. Uj first comes with all the terms of this sum. So you should first write the sum outside, and then you should write inner products as the terms of that sum, where the ith term would be this inner product, the inner product of uj and this thing, this term, except the sum, only this vector, this scalar times this ui. And then from that inner product, the scalar comes out. But because it is coming out from the second component, so the scalar itself does not come out, but its complex conjugate comes out. Already there is a complex conjugate, so that is why you see this ordinary ui t comma v. And then with that, what else do you have? You have uj with ui, this inner product. This is the conjugate linearity of inner product in the second variable, which tells you that if a scalar comes out of the second variable means second component, this is the first component, this is the second component. If a scalar comes out of second component, then the scalar does not come out as it is. Its complex conjugate comes out. So that's how we have this. Now in this sum, j is fixed. Actually, j is not dead fixed in the sense that j is not exactly just 1 or anything like that. But once you have chosen j is fixed. So in this sum, I is varying but j is fixed. Now you look at these inner products, okay, as I varies. Of course, along with them you also have these things, but as I varies, what happens to this inner product? Keep in mind that we are working with vectors which form an orthonormal basis. So that is why these inner products will be 0 if I is different from j. But if I is equal to j, then it will be 1. So most of the terms of this sum vanish. There is only one term which survives, so to speak, and that happens when I is equal to j. And in that case, this becomes 1, and when I is j, this is what you are left with, uj t comma v. So is it not what you wanted to show? Yes, it is that equation which we have now proved for any basis vector uj. So we have proved that our equation is true for basis vectors, but then automatically it's true for all the vectors as we saw previously. So we have proved half of the result, but now we also need to prove that this w is uniquely determined by v and t. So that uniqueness part is still there. So now next what we do, we are going to use the fact that these two things are equal and consider this inner product of u with w1 minus w2. By the linearity properties of inner product, you already know these things. This equals u comma w1, this inner product, minus u comma w2. And because these two are equal, this becomes 0. And do not forget that this is still true for all u belonging to v, because u is still there here. So that is why in particular, in place of u, we can also consider the vector w1 minus w2 itself and get the fact that the vector is orthogonal to itself. Its inner product with itself is 0. However, we know that that only happens for the 0 vector. So this must be the 0 vector, and that's how we get w1 equal to w2. So yes, the w that we proposed, which we also saw works, I mean it satisfies that equation, is the only w. It's uniquely determined by that vector v and the linear operator t. So here the proof ends, and now this result is going to give us the notion of Hermitian adjoint. Let's see how. And this is the definition of Hermitian adjoint of a linear operator. Let T be a linear operator on a finite dimensional inner product space V, same setup. Then the Hermitian adjoint of T, written as this, T star, is defined by this equation. The inner product of ut and v equals the inner product of u and v t star for all u and v belonging to v. It's very confusing, no? I mean, we are defining possibly another linear operator t star like t. However, we are not saying directly what t star does to a vector. We do see the image of this vector v under t star here. This notation means the image of v under t star. But we are saying that it is such a vector which should satisfy this equation. We are not directly saying what the image is, but we are indirectly saying that it is one such vector which will satisfy this equation. But that raises two questions. What is this vector? Does it even exist? That is the first question. And the second question is it unique? We have to answer these two questions. What did we just now see in that lemma that we proved today? That for any v in V, there exists a unique w in V such that ut, v equals u, w. For a given v, there is a unique w for which this equation is true. T is already there, okay. And this w is actually what we are saying this Vt star is by definition. So for a given v, not only does a w exist for which you see same equation, the only difference is that here you have Vt star and here you have w. So this is what we are doing to define T star. If you really want to write a definition for this function T star, it's after all a function from the vector space V into itself, it will be this: Vt star is defined to be equal to W. So instead of saying it like that, we are saying it in using this equation, because actually that's where W comes from. So not only does a W exist in V for which this equation will be true if we have W in place of this, but that W is unique also. So for every input V, there exists a unique output W. So T star is a well-defined function with V as both the domain and codomain. That does not, however, say immediately that T star itself is also a linear operator like T. Those things are there, that is also true, but that does not follow from this definition. However, now the definition is clear, and such a function T star is called the Hermitian adjoint of that operator T. Now let's see some properties of this T star. This next lemma, lemma 6.10.4, gives us some properties of this star. If T is an operator on V, linear operator, then T star, yes, is also a linear operator on V, as we were suspecting right now. So that makes this star itself a function from A of V into A of V. It takes as its input any operator T coming from the algebra A of V and gives the Hermitian adjoint of that operator as the output. Moreover, for any operators S and T on V and any scalar lambda, these things are true. If you take Hermitian adjoint 2 times on T, you get T back. The Hermitian adjoint of S plus T equals the sum of their Hermitian adjoints. The Hermitian adjoint of the scalar multiple lambda S of the operator S by the scalar lambda equals the complex conjugate of lambda times the Hermitian adjoint of S. And finally, it also interacts with multiplication of operators, which is also available to us because we are in an algebra. The Hermitian adjoint of ST equals the product of their Hermitian adjoints, but in the other order. The things get flipped. T comes first, followed by S. T star, S star. We will prove it in the next video.